So now we're going to go over the dependent t-test. The difference between the dependent and independent t-test is that in the dependent t-test, the two groups are dependent on one another, meaning that they're paired or that one score is a before then after score type thing. There are two scores and they're dependent on each other. They're not independent. Another way we call this is the paired samples t-test. So for this chapter, we're going to be working with data again from the LSJ data set. So we're going to go to the menu, open, and in the data library, we are looking for the Chico data set. So Chico, not Chico 2, so we'll check the first one. And we can see our data here. We have our student ID variable, which is just their number, and their grade after the first test, or grade from the first test, I should say, and their grade from the second test. And in this case, we're interested in knowing whether the students work harder on the second test and therefore do better on the second test. That's the hypothesis that Dr. Chico has. So again, we need to double check all of this. This isn't quite correct. A nominal variable, a textual nominal variable is close, but more accurate would be to say that this is an ID variable. So we're just going to make that change. It's already accurately figuring out that these are two continuous variables, so we're good to go. Our data is set up and ready for us to perform our statistical analysis. So our first step is always to look at the data, so I always go to exploration and descriptives to look at it. And we have two continuous variables, so they go into the variables box. And we can always change if we want them by row or by column, so I kind of like this view better. It's when there's only a couple variables, so we'll click that. We can get our skew and kurtosis here in the Shapiro-Wilks if we'd like. And then I always love to have my box plots. So we can see our box plot of the first variable looks fairly normally distributed, but again, we only have, what was it? Go back to our data. We only have 20 students, so not much there in the first place. And they're both fairly normally distributed, as we can see from the kind of shape of the distribution of the data. We also have all this information, and so we could pull over and look at Shapiro-Wilks. It's not statistically significant, so it looks like our data is normally distributed. I'm going to open up my calculator so we could just check skew and kurtosis while we're here. 0.06 divided by 0.51. 0.12, that is less than our cutoff of 1.96, so that's good. 0.28 divided by 0.99, 0.28, again, good. So normality is looking pretty good here. Okay, so the problem though is that's testing the normality of the two variables. That's not quite the assumption of the dependent t-test. The dependent t-test has more of an assumption that the differences between the scores are normally distributed. And that's because technically what's happening is it's kind of like an independent t-test. We have the independent variable as the 2 time points, and then the dependent variable is the score at each time point. And so, but we have to tell it that it's paired, and that's why it's like that. But we could kind of convert this to be a long format. This is called wide format. If we changed it to long format, that would make sense. And then we could calculate the difference between the scores, and that's what we want to test. We could also just check it ourselves. So let's just do that real quick. We're going to compute a new variable. Can I move this over? No. I'll just click here and commute, just so it's over here. So test 1 minus test 2, let's just say, okay? And that's going to be grade test 1 minus grade test 2. Click enter, and those are our different scores. So we could go back here and add our new variable into there, and now we're checking the normality of our difference score. So our mean of the difference, the average mean difference, is negative 1.4, meaning, actually it probably would make more sense to go the other way, right? So we could change that real quick. Test 2 minus test 1. Meaning that students have an average of 1.4 points higher on the second test than the first test. Is that statistically significant? Don't know yet. We haven't performed the test. And this is where we want to check. So 0.51 divided by 0.51, that's 1, so that's fine. And we could check our other one. Let's see, I close that. 1.10 divided by 0.99, that's 1.11. Both of those are under our threshold of 1.96, therefore we meet the assumption via skew and kurtosis. As well, our Shapiro-Wilks is not statistically significant. And lastly, we can look at our difference scores, nice and normally distributed. So we meet the assumption of normality. There will be one more check that we can get in the t-test, I think. Yeah, it'll show us the QQ plot, which, why don't we have that here? Oh, right, QQ plot, there we go. QQ plot, we meet the assumption, good. So now we can go check our other assumptions, which is that is the data interval or ratio? Well, we already looked here. Technically our difference scores are continuous, so we're good. And so are our scores independent across participants, meaning this person is different than this person? Pretty likely that that's the case. So we're going to say that we meet that assumption as well. So now let's go perform the test. So under analyses, under t-tests, we click paired samples t-test, right? Same name for the same test. Dependent and paired samples t-test are the same thing. Our paired variables are test 1 and test 2. So you could click one in and then click the other one in, or you can click shift or control and bring it over like that. Either way. Right now we're going to assume we've met the assumption and just click students, but if we don't meet the assumption normality, then we click Wilcoxon. I like to choose all of the additional statistics. We'll just check those assumptions one more time. But we need to check our hypothesis. Remember, Dr. Chico seems to think that test 2 students will perform better on than test 1, meaning measure 2 is higher than measure 1. And that would be this third hypothesis. So you need to make sure that you change your hypothesis depending on whether it's a one-tailed or two-tailed test and what direction if it's a one-tailed test. So that's it. Those are all of our options that we need to choose. And now we can look at our data. Again, we could check normality. P-value is not statistically significant. QQ plot looks good. Awesome. So now we can look at the statistical results. So again, our mean difference was 1.4. And the statistic is 6.48, and our p-value is less than 0.05. So we have a statistically significant difference between test 1 scores and test 2 scores. The only reason this is negative is because I put test 1 first and then test 2. And that's because test 1 has lower scores than test 2. So that's what the negative means, that it's lower at test 1 than test 2. Watch what happens if I do test 2, then test 1. It's now positive. It's not negative anymore. And that's because test 2 scores are higher than test 1. But there's an error, right? Why isn't our p-value the same? And that's because our null hypothesis is incorrect. We need to flip it. So now it's measure 1 is greater than measure 2. So test 2 is greater than test 1, right? A little confusing, but you can do it either way. And just note that the negative doesn't really matter for the t-test. So statistically significant difference between the two, it's a 1.4 point difference. And the Cohen's d is 1.45, which is a pretty darn big effect, even though the mean difference looks pretty small. We can look at the plots, but again, I don't quite like this plot. And so I'm going to walk you through how to do the plot that I prefer on here. And I'm going to copy from the textbook. Oops. Yeah, remember that you can always go in here and change all this stuff up. We are going to go into the RJ editor. There we go. And I may need to change this. I think this will be fine. Okay, so we're going to paste all this. So our data is data. We're changing all that. We're changing the columns 2 and 3. Columns 2 and 3. Whoops. Go back here. Here we go. The variable names are called test score, and the time variable is test time. And so now then we need to look at the descriptions here of and this is the formula. So let's run this, see what happens. I figured out what happened. Don't know what happened really. It just didn't like this instant of RJ editor. I just started a new instant of RJ editor, just click this and click this again. But now it's working just fine. So if you're having this error and it's just being weird, just start fresh, right? We can just delete this analysis, remove that analysis. This one's working with the thing that I copy pasted. So it'll give me the descriptives because I asked for it through here. I don't know how to turn that off, but that's fine because here's our figure. And so we have test score on the y-axis, test time on the x-axis, test 1 or test 2. Perfect. This is great. And now this is a much better plot of our data than this one. This is not a good plot. This is much better. And so we can just export that image and put that in our report.